Here's the game. You get to color every single point on this infinite plane, everyone, using just two colors, red or green. There's exactly one rule you have to follow. Anytime you pick 3 points of the same color that are not collinear, any three, the very center of the circle that passes through all three has to be that same color too. That's it. That's the whole rule. So here's the question. Can you actually pull this off? Can red and green live together on this plane forever? Both surviving, both obeying this rule everywhere? Or does this one small rule secretly force the entire plane into a single color? Stick with me, because it does. And the way you prove it is genuinely beautiful. At first glance, it doesn't seem impossible. Surely there should be some clever way to mix red and green without ever breaking the rule. The challenge is that this isn't about coloring a handful of points, it's every single point on an infinite plane. So where would you even start? Well, probably with the simplest ideas. Before trying to prove anything, let's see if we can actually invent a coloring that works. What if we split the plane in half, red on the left, green on the right? But then, if you take 3 red points close to the boundary, draw the circle through them, the center that must be red lands on the green side. Rule broken immediately. So this can't be a valid coloring. Okay, what if red is just a small island, a disk, and green is everywhere else? Same problem. Pick 3 green points on the green region around the island, and the circle's center falls right inside the island. Strips. Checkerboard. Same story every time. Every clean, simple way to split the plane into 2 colors seems to immediately break the rule. So maybe the real question isn't how do we find valid 2 coloring. Maybe there isn't one. Let's try to prove that. Here's our strategy. Proof by contradiction. Let's just assume for the sake of argument that both colors really do exist somewhere on this plane. Doesn't matter where. Just pick any red point, call it P1, and any green point anywhere else at all, call it P2. That's the entire assumption. Just these 2 points, we are about to show that they're enough, all by themselves, to unravel the entire coloring. Now we build. Take P1 and P2 and find the 2 points that complete an equilateral triangle with them, one on each side. Call them P3 and P4. Could P3 and P4 both be red? Watch. The circle through P1, P3 and P4 is centered exactly at P2. Since P2 is green, if all 3 of those points were red, the rule would force P2 to be red too. But P2 is green, that's a contradiction. So they can't both be red. By the exact same logic, they can't both be green either. That circle centers on P1, which is red. So one of them is red and one is green. Let's say P3 is red and P4 is green. It doesn't matter which. The argument works either way. And notice something important. We didn't choose these colors. The rule forced them on us. That's our whole strategy from here on. Keep building points whose colors are forced, not chosen, and see where it leads. Start by reflecting P2 across the line through P1 and P4. Call the result P5. Could P5 be green? Look at the circle through P2, P4 and P5. It's centered on P1. P1 is red. If P5 were green, then P2, P4 and P5, 3 green points, would force their center P1 to be green too. But P1 is red. So P5 can't be green. It's forced red. Now we continue. And this is where the trap really starts closing in. Reflect P1 across the line through P4 and P5, call it P6. And reflect P1 across the line through P2 and P4, call that one P7. Here's the payoff. All 4 of these points, P1, P5, P6 and P7, sit on a single circle. And that circle is centered on P4. P4 is green. So neither P6 nor P7 can be red. If either one were, we would have 3 red points on this circle, forcing green P4 to become red. So both are forced green. One more to go. Reflect P1 across the line through P2 and P3. Call it P8. Same move as before, just faster now. The circle through P1, P3 and P8 centers on P2, which is green, so P8 can't be red. It's forced green. Now step back. Look at what we've built. 8 points. Apart from the 2 we started with, every color was forced by the rule. Now draw one last circle. P6, P7 and P8, all 3 green. Watch where the center of that circle lands. Exactly where this whole story began. P1. 3 green points forcing their center to be green. But P1 is red. We picked it that way all the way back at the start. A single point that has to be both red and green, that's impossible. That's a contradiction in its purest form. So what actually broke? Our only assumption was that a red point and a green point both existed somewhere on this plane. That's it. That one assumption is what led to this contradiction. Which means the assumption itself has to be false. Both colors cannot exist at the same time, not anywhere. So the plane isn't half green or are striped or islands within islands, it's one color. Entirely, every single point. It might be completely red or completely green. Doesn't matter. Now I have to tell you something. This wasn't just a puzzle I made up. This exact problem was problem B1 on the 2025 Putnam Competition held this past December. If you've never heard of it, the Putnam is the most prestigious math competition in North America for college students. 6 hours, 12 brutal problems, and the median score most years is 0 or 1 point out of a possible 120. Thousands of students sit this exam every year, and only a handful in its entire history have ever scored a perfect 120. And here's something genuinely interesting. Researchers evaluated some of today's best AI language models on this year's Putnam. The top system scored 103 out of 120. Good enough to place in the top 3 out of over 4,000 human competitors. These models are, by any reasonable measure, excellent at this exam. But when researchers compared problem by problem performance, one problem stood out from all 12. B1, our problem, had the single biggest gap between how easy it was for humans and how hard it was for the models. Humans ranked it the easiest problem on the entire exam. The models ranked it the 9th or 10th hardest. So if you followed that argument all the way through, the reflections, the forced colors, the trap closing on P1, you just did something that this past December, a lot of very talented people found genuinely difficult. And even AI systems that were otherwise acing this exam stumbled on it, relatively speaking. Now here's the idea I want you to walk away with. We never needed to know anything about the actual coloring of the plane. We just needed one red point and one green point to exist. And that single tiny assumption was enough to snowball into an unavoidable contradiction, 8 points later. This is called a rigidity argument, and it shows up everywhere in math. A small local constraint chained together enough times ends up pinning down the entire global structure. So here's a challenge, if you want one. Try inventing your own coloring. Maybe 4 colors instead of 2. Maybe 4 non-collinear points on a circle instead of 3. See if it's secretly rigid too. I promise you will be shocked to know the answer. Thanks for watching. I'll see you in the next one.